So the test covers these basic 4 topics: finding arc length, finding surface area with 3-dimensional shape, using calculus to determine probability, and solving separational equations. That's 8.1, 8.2, 8.5, and 9.3. There's 3 of every question, so there's 12 total questions on this test. This is the arc length formula. So that's the formula we're going to use for 3 of them. I think the key with this one is literally just remembering, like figuring out, is it going to be mixed up? So it's figuring out what the question's asking you and then finding the equation for it. Remember, you are allowed to use a sheet of paper. So I would just suggest writing down the formulas and stuff that you're going to need on them. I've got them set up on here, so you're going to actually see them before we actually do the problems on them.
Can you go back a page for a second?
Sure.
Thank you. Now, when you say solving separatable equations, that's differential?
Yep, that's the differential equations. It's just a very specific differential equation. That's why I didn't put just differential equations there. So the specific version is these I can actually take and split up the x and the y to solve each one independently. That's why they're called separatable. All right, so there's the arc length formula. It's the square root from a to b, or the square root, the integral from a to b of the square root of 1 plus the derivative of y squared dx. All right, so let's look at this one. So yeah, one thing you do want to keep in mind is when if you read these, if it says use a calculator, use a calculator, because that most likely means you cannot do the problem out by hand with what you have. So we've got our equation. So set up my integral. So I have the integral from 1 to 4 of the square root 1 plus, and then I've got to find the derivative of the dx, the dy dx. So my derivative of this, so I've got, oh, actually it's dx dy. So we've got the square root of y minus 8y. So we do the derivative of the square root of y, which comes out to be 1 over 2 square root of y. And then the derivative of 8y is just 8. So that's dx dy. So it was dx dy squared dy. Any questions with the derivative there? Now we just plug it into the integral. Since this one says use a calculator, we're going to use Desmos for this one. So remember, you have to use the graphing calculator for this. And if you click on the little keyboard thing at the bottom, go to integral, calculus, and my integral's right there. So we're doing it from 1 to 4. And then it's square root 1 plus dy.
Good question, Professor. When you square a negative exponent, for example, say we were to actually FOIL that out, what would
Yep.
the a and a term equal to? So it would be like 1/4 times, and then you would just add the 1/2 plus 1 minus 1/2, so it would just be y to the negative 1.
Yeah, it would be negative one. It'd still be y to the negative 1.
Okay, so you just add the two minuses, which is just minus 1/2 minus 1/2.
Well, no, actually, when you in the middle term.
If you were, for example, just for the sake of
So,
math.
okay, hold on. I'll show you, then I'm going to delete this. It's not really part of the whole thing, but that's okay. So we've got, hold on. I can write it down again. So we got 1/2 square root of y minus 8 squared.
Right, just the first term. You don't need to do it all out. So a times
So
a.
the first one is just, it's going to be 1/4 y to the negative 1.
Okay, that's all I wanted to confirm. Thank you.
Yeah. Because it doesn't actually, like, it doesn't do anything else to it. It's just because it's, in essence, it's y to the negative 1/2. So you're squaring it, it becomes the negative 1. All right. So did this one on the calculator. The answer is 23.1. What is that? What did they say? Round to the nearest 4 decimal places. So the answer is 23.1948. And that's the final answer for it. Any questions on that one? Yeah, I wouldn't use like integral calculator and stuff for these just because it's going to give you a ton of extra steps that you don't really need. The Desmos calculator works actually really, really well for these just to get the answer. And just keep in mind, like if you put X here, it wouldn't have mattered. Just make sure your the number at the letter at the end is the same. So if you had put the X there instead of the Y, just make sure it's DX at the end. It won't actually change the answer or anything else. And you have to put the dy at the end, otherwise it won't actually give you the answer. All right, next one. This one's finding the exact length. So this one, we're not using a calculator for. They want the exact length for it. So remember, thing. So the first thing I have to do is find my derivative. So the y is that. So the dy dx. The 5 disappears. And this becomes 24/2, which is 12x to the 1/2. Remember the derivative, you're bringing down the exponent and then subtracting 1. Unlike the integral where you're adding 1 and then flipping the exponent over. So really easy thing to screw up, especially when you're going back and forth. So the 3/2 is coming down and multiplying by the 8, which is how I get the 12. So we're going from 0 to 1. So it's 1 plus 12x to the 1/2 squared dx. So it's 1 plus 144x dx. So now in this one, we've got a function inside of the square root, so I've got to do a u substitution. So if I make u 1 plus 144x, du is 144 dx. So it's 1 over 144 du equals dx. So I got the 144 up front. And it's just the square root of u du. So 144. Bring down the, so it's times 2/3 the u to the 3/2. So it's 144. Or actually, let me actually multiply those out. So it's 216. And then 1 plus 144 x to the 3/2, all evaluated from 0 to 1. So the 0, 1 is going to be just 1. When I plug in the 1, I get 145. So it's the 145 to the 3/2 minus 1 all over 216. I know that's not the way they write the answer, but they'll take it. Any questions with that one? So that one was pretty straightforward. Just a quick u substitution. All right. Next one, same concept. I'm still doing a simple arc length problem. The work inside of it just becomes a little more complicated because it's got the secant stuff in it. So B all right, so in this one, I've got y equals the ln of the secant of x. I need to do the derivative of that. Anybody want to tell me what rule I need to use?
Liate,
Huh?
Liate.
No. So if we were doing the integral, then yes, I probably would have to use integration by parts. But I'm doing
You use the chain rule?
yes, we have to use the chain rule for this one. So what's the derivative of secant of x? Because the chain rule says do the inside and then do the outside based on if it was just gone. So what's the derivative of secant of x?
That's secant x plus tan x or something like
Secant
that.
x, tangent x. No plus, just both of them.
Got it.
And then the derivative of ln of x is just 1 over that, right? So it's going to be 1 over secant of x. So my derivative actually ends up being just tan x.
Okay, so just to kind of chain rule it up real quick. So the so the derivative of ln of x was just 1 over x, and obviously the x in this point is secant of x. So
Yep.
that's cool.
So that's that. Technically the whole thing, which is just not done. All right, so go back over here. Let's plug all my information in. So I have 0 to pi over 6. And then I have 1 plus tangent squared x dx. 1 plus tangent squared x is the same thing as saying secant squared x. So that right there is secant squared x. So this is the integral from 0 to pi over 6 of secant x dx. And that one was one of those rules that one of the basic identity rules type things that you just have to kind of remember or write down. So this ends up being ln of secant x plus tangent x. And we're evaluating that from 0 to pi over 6.
Wait, sure. What happened to the square root?
The square root of secant squared x is just secant x.
Oh, okay, my bad.
Oh, you're fine.
So that's just one of those things we just have to remember. The integral of secant is ln
Is
of
that.
secant.
Yep.
Is it within our realm to know how to prove that? Or
No. There actually is. It's integration, but actually, we did one similar. We did the secant to the third x. We did it by integration by parts, but this one is it's just one of those identities. It's kind of like saying the integral of sine is cosine. It's like why? Because that's the way it works. So this is one of those ones that an elementary rule that you just have to kind of remember. All right, so now we've got to plug in our values. So we've got secant of pi over 6. So I've got ln of 2 over the square root of 3. Actually, 2 square root of 3 over 3 plus tangent which is square root of 3 over 3. And then minus ln of secant of 0, which is 1, I think.
Yes, which makes it 0.
Yeah.
Question, if I leave it as tan pi over 6 plus secant pi over 6, is that wrong?
I do not know the answer to that.
I have one that's tan pi over 3 when I did the example and it took it. I don't
Okay.
know if it bothers you.
Oh, if it's gonna take, like, I'm one of those ones that, like, that's fine. It's
Okay, I know them, but I hate remembering them. And it's extra time I don't want to waste, like just going through and doing that.
yeah. I didn't. I know. I
Okay.
wasn't sitting there looking it back up either. So I literally typed them in because I'm like, I'm just not gonna go look them up right now. It's fine. So this one actually becomes a little simpler because you can put those two together. So this ends up being just ln of the square root of 3, if I'm right. Yeah, this one ends up being just the ln of the square root of 3.
Could we please work that out? Wow. From just like from the beginning there, I'm looking at my unit circle and that pi over 6, the x value is square root of 3 over 2, right?
Yep.
And then the y value is 1/2. So.
Right, but secant, so secant is the reciprocal of cosine. So that's your x value. So it's the
Right.
reciprocal of square root of 3 over 2, which is 2 square root of 3 over 3. Because you end up getting the 2 over the square root of 3, which you rationalize. And
It's
then
hypotenuse over,
right. So
over adjacent.
yeah. So cosine of pi over 6 is square root of 3 over 2. So if you flip that for the secant, is 2 over the square root of 3, which is 2 square root of 3 over 3. Tangent of pi over 6 is 1/2 over the square root of 3 over 2.
So are you showing us?
Oh, darn it, wrong screen. I always forget to switch the right one. So there's cosine. Cosine of pi over 6 is square root of 3 over 2. And the secant's the reciprocal of it. So it's 2 over the square root of 3. So that's 2 square root of 3 over 3. Tangent is 1/2 times 2 over the square root of 3, which is 1 over the square root of 3, which is square root of 3 over 3. See, I can do it. I was just being lazy.
Yeah, so if you were to draw out the triangle, just for the sake of clarity there, yeah, pi over 6, right? It's 1/2, right? The cosine is typically adjacent over hypotenuse, right? So it would be hypotenuse over adjacent.
Right. So it's 1 over the square root of 3 over 2.
Got it. Okay. So, oh, so is rationalizing just making sure that there's no square roots at the
Square root on the
bottom?
bottom. Correct.
Okay. Do they care about? I mean, does it matter?
I'm not sure if WebAssign cares. I know there's a lot of professors that truly care. So if you're going forward, I would definitely get into the habit of rationalizing your denominators. It's not a big pet peeve of mine, but it's a really big pet peeve of some people. It's also one of those things that when you're looking at like a problem like this one, like by rationalizing it, it really is simpler to put the things together. Like if these weren't rationalized, it would have been a lot harder for you to get to the ln of square root of 3.
Oh, the hypotenuse is always, oh yeah, the hypotenuse is always 1 because it's a unit circle, right?
Correct. Yep.
Thank you.
No problem. All right. On to surface area. So here's surface area. Here's the basic formula for it. Remember that y is really your radius. So depending on how we're rotating it, depends on which, or depending on what my radius is, depends on what that's going to be. It can either be x or it could be the y. Or the y is the function, I should say. So that really just depends on how we're rotating it. So let's look at this one. So this one, we're rotating around the x-axis. So my radius, so if we're looking here, if we just like do a quick little sketch of it, that right there is my radius. So my radius is the y value. So that's my equation. So my equation from A to B of 2 pi y, the square root of 1 plus dy dx squared. So again, the first thing I have to do, I have to find my derivative and then go through and clean up my square root part basically before I actually do the integration. So the dy dx of this will be x squared over 2. And then minus 1 minus, yeah, 1 over 2x squared. So if we do that squared, we get x to the 4th over 4 minus 1/2 plus 1 over 4x squared, or to the 4th. And then if I'm taking that and I'm adding the 1 to it for the square root, we get x to the 4th over 4 minus, or plus 1/2 plus 1 over 4x to the 4th. So we end up getting just my original part squared. So we do the factor into that one out. So my square root is going to basically cancel that part out. So my integral is from 1/2 to 1. We'll pull out the 2 pi. I have x to the 3rd over 6 plus 1 over 2x times x squared over 2 plus 1 over 2x squared. Yeah. That part makes sense? So this is the simplification of that square root part. Again, when you're looking at these problems, realize that unless they're telling you to use a calculator for it, they're probably going to come out to be something you can do easily enough. So when you get something like this, you probably are going to be able to factor it down to get rid of your square root. All right, so we're here. Now we have to FOIL. So I've got x to the 5th over 12 plus x over 12 plus x over 4 plus 1 over 4x to the third. So x to the fifth over 12 plus x over 3 plus 1 over 4x to the third. Now we can do our integration. So x to the sixth over 72, x squared over 6, minus 1 over 8x squared. And we're dividing it from 1/2 to 1. All right, so we've got 1 over 72 plus 1 over 6 minus 1 over 8. Minus 2 to the 6th power is that 72? No, 64. Heck, 64 times 72. Jeez. They really wanted to make these tough, didn't they? All right, so I've got 1 over 4,608 minus 1 over 24 minus, or actually plus 1/2.
So now, is this something we can just plug into the calculator to avoid having to deal with all these?
Yes.
Okay. What's the LCD with 4608, you know?
Yeah, that's actually literally what I'm about to do. Is I'm just going to go to the calculator and do it out real quick because I'm not doing this off by hand. Oh, I don't want that. Actually, I can do that. 1 over 72 plus 1 over 6 minus 1 over it plus 1 over 6 minus 1 over 8 minus 1 over 468 minus 1 over 4 plus 1 over 2. It's not going to give it to me as a darn it. Oh, yeah, and the whole thing is times 2 because of the pi. So 263 over 256 pi. All right,
So we just divided by pi there at the end.
pi. Because this whole thing was multiplied by 2 pi.
Could you go back to the calculator? Just to decimals.
Notice I did not put the pi in here. Because if you put pi in there, it's not going to give it to you as a fraction. I'll give it to you as a decimal. See if I put pi in there. See, that gives it to you as a decimal. But by not putting pi, it gives it to you as a fraction. And then you just put pi next to it because it's that times pi. That, all right. Two more surface area problems. So this one, same process. This one is also rotating around the x-axis. So since we're rotating around the x-axis, my y is going to be my radius. So, or in this case, actually, no. In this case, actually, my y is going to be my radius, but since we're solved for x, I'm still going to use y as my radius. I don't have to use the equation for it. So first thing I have to do, again, I have to find my, so I've got 2 pi a to b y square root of 1 plus d, or dy dx squared dy. So I got to do my derivative. This one we're also going to have to do the chain rule for because I have a function inside of a function. So the dy dx or the dx dy. I have 1/3. The derivative of the piece inside is 2y. And then if I do the derivative of that, if it was just y to the 3/2, I get 3/2 y squared plus 2 to the 1/2. So if I simplify all this down, I have y and then the square root of y squared plus 2.
Wait,
So,
sorry, I'm confused as to how you work that derivative out.
so it's the derivative of the y squared plus 2, which is 2i.
The chain rule again.
Right. And then it was the derivative of just u, like u to the 3/2, which is 3/2 u to the 1/2. And that u was y squared plus 2. That's the chain rule. So now I'm doing the 1 plus y squared of y squared plus 2 squared. So it's 1 plus y squared times y squared plus 2. So I've got y to the fourth plus 2y squared plus 1, which factors out to y squared plus 1 squared. That makes sense? One to 4 y times y squared plus 1 dy.
Hey, Professor, how did we get rid of the second y there? 'Cause it was
This y?
in the top left, there's a 2y that we started off with, and then the,
I didn't get rid of the y, I get rid of the 2 because it's 1/3 times 2 times 3/2, which is just 1. The y is still there.
uh, oh, okay.
So I did 1/3 times 2y, which is 2/3 y times 3/2, which is just y.
Got it.
All right. So the y up front, that's still my radius. My square root was just the square root of y squared plus 1 squared, so that's just the y squared plus 1. So I can multiply this out and then do my integral. So I have y to the third plus y dy. So 2 pi y to the fourth over 4 plus y squared over 2. And we're evaluating it from 1 to 4. So I got 2 pi 4 to the fourth. Much it's 4 to the 4/3, 64. Plus 8 minus 1/4 minus 1/2.
Professor, I'm just a little confused. Why is it y is just y the whole way through on this one? I know usually we like change it.
Right. So in this one, we're rotating it around the x-axis. So
Mhm.
again, but the problem is actually, you know what? I'll do this in Desmos. I'll show you the equation because it's actually gonna
Okay, I think I get it now because it's around the x-axis, but it's solved for x.
yeah.
The
So
y value is going to be your rotation.
so
Okay. Your
but
ra-
let me
your
actually
radius.
show it. So oh, darn it. So basically, remember, we're rotating this around the x-axis. So my radius is still y. If I was rotating it around the y-axis, my radius would have been the x, which would have been that equation. So that's why it all comes down to what is your radius. In this case, my radius is still y, but since my equation solved for y, I can just use y instead of having to plug the equation in like I did in the last problem.
Got it. Makes sense.
Okay. All right. One more of these.
Wait 1 second. Could you go back? I'm gonna take a photo of that workout for a second. Thank you. Cheers. Great, got it.
All right, so this one's given the curve rotated around the y-axis. The area of the resulting surface is this. So in this case, when I'm doing it, I still have my 2 pi, a to b. This one, my radius is going to be, in this case, my radius is going to be x. Because we're going around the y-axis, so it's going to be x out is going to be my radius. Does that make sense?
Yes.
All right, so same thing. Still got to find my derivative of this. So dy dx is 1/2 x minus 1 over 2x. So we're going to square it. So I've got x squared over 4 minus 1/2 plus 1 over 4x squared. If I add the 1, I get x squared over 4 plus 1/2 plus 1 over 4x squared, which then I can factor it, and I get x over 2 plus 1 over 2 squared. So my integral from 4 to 5 of x times x over 2 plus 1 over 2x dx. All right, everybody see how I went from that step to that step? I just pulled out the 1/2. We have 4 over 5. 1. So the integral of that is x to the 3rd over 3 plus x, and we're valuing from 4 to 5. So pi 125 over 3 plus 5 minus 64 over 3 plus 4 minus 4. So 61 plus 3. So it's 64 over 3. So 64 over 3 pi. All right, any questions on surface area or arc length before we move on to probability? All right. Probability. So we have our probability density function, which is just the integral from a to b of the f of x. So whatever the function happens to be. We have our exponential density curve, which is just see where the intercept is, or if we're looking for the mean, we have it in terms of the mean. And if I have a normal distribution, that's the curve for the normal distribution. I'd have those written down somewhere. Because the first thing every one of these is going to ask you to do is to write out the equation. All right, everybody got this down or taking a nice little picture of it? All right. So this one tells you a light bulb is labeled as having an average lifetime of 1,000 hours. It's reasonable to model the probability of the failure of these bulbs by an exponential density function with a mean of 1,000. So we're going to use the exponential density function, which is this one, and we're going to do it with the mean. So we're using that formula. So remember, you don't really have to worry about the zero part of it because that's kind of assumed. So we've got f of t equals 1 over 1,000 e to the negative t over 1,000. And the first equation, first one says within the first 400 hours. So for AI, we're doing the integral from 0 to 400 of 1 over 1,000 e to the negative t over 1,000. dt.
Why don't we have to use the rest of the equation again? The 2 pi, all of that.
We're not doing surface area.
No. On the previous slide, there was the 1 over, forget what that's called, times.
Oh,
the
this?
square root, 2 pi, yeah.
That's for the normal distribution.
Oh, okay, for normal.
So this one specifically says exponential density function.
Got it.
So, and I totally didn't switch over. Yeah, that's normal distribution. This is the exponential density function. All right, so do my integral. And then the nice thing is the integral is the same one for the first two, so we don't have to try to do it actually twice. And we're actually going to be able to use it for B too. So let's do my integral for this. The nice thing is, so this one you're going to have to do a U substitution for it. I'm just going to make U my negative t over 1,000. So U is negative t over 1,000. So du is negative 1 over 1,000 dt. So the only thing different is the negative sign. So this integral, or the answer, ends up coming out to be negative e to the negative t over 1,000. And we're evaluating this from 0 to 400.
So du or dt equals negative 1,000 du, right?
dt equals 1 over 1,000 dt. The negative sign you're actually moving over here, which is why there's a negative sign there. And the 1 over 1,000 disappears.
I see.
So now we're going to use a calculator. See, it says round to the answer to 3 decimal places. That means calculator use. So for this one, I would it doesn't actually make much difference if you use the graphing calculator or the scientific calculator because we want it as a decimal. So I just use the graphing one at this point. So we've got negative e to the negative 500 over 1,000. And there's a reason I'm writing this all out, even though, actually, wait, I missed the negative sign. Negative, and then plus e to the negative 0 over 1,000. The reason I'm writing it all out is because we basically have to use the exact same thing to do the next one. So
Is it 400 or 500?
Oh, was it 400? It was 400, right? Another nice reason to have it on the calculator, quick and easy to change. So this one comes out to be, so the first one is 0.330 when you're rounding to 3 decimal places.
So e to the 0 is just
That's
one,
just
right?
one.
So you're just adding one there.
Yeah, that's just one. The reason I put it in there is because the next one I'm gonna have to use it. So I figured having it there, this way I'm just gonna literally be able to retype a number in there. So the next one says, use this model probability to find a bulb that burns for more than 1,000 hours. So in this case, this over here is gonna be infinity, which I can't actually write, but that's okay. So that'll be infinity. E to the infinite or negative infinity power is what?
Right.
It's 0. It's gone. So then I can put 1,000 up there. So this one comes out to be 0.368. AI. So then the second one was negative e to the negative t over 1,000 from 1,000 to the limit as t goes to infinity, which is 0.
So are those the final answers, 0.330 and 0.368?
Yep. All right. The B part of this one says, what's the median lifetime of these bulbs? So median means what's the answer going to be? What's the probability that it's going to be in the median? What's right in the middle of my curve?
500.
Right. Point or not. Well, not 500 hours because I don't know. So median is going to be 50%. So 50% is going to be on one side, 50% is going to be on the other side. Okay. So the goal is this problem is to figure out where that happens to be. So my integral doesn't actually change. What changes is I don't know what t is. I actually have to figure out. So in this case, I'm doing it from 0 to m, and that has to equal 0.5. So I have e to the negative m over 1,000 plus 1 equals 0.5. That makes sense? So we're looking for a value that's going to give me, the answer would have been 0.5 if I did it in this problem here. What number here is going to give me 0.5 as my answer?
So it would be 1,000 negative 1,000 ln of 0.5.
There, I can get rid of the signs. So yeah, it's ended up being. I'm gonna have to go on this slide. Ran out of room. So e to the negative m over 1,000. 5. So we do ln of both sides. So I get negative m over 1,000 equals ln of 0.5. So I get negative m equals 1,000 times ln of 0.5. So it's the negative version of that. So now we go back to our calculator. And I do negative ln and we get 693, and it wants it to the nearest 1 decimal place, 0.1 hours. So it's the nice thing about these problems is you're only going to do your integral once, and then you're going to use that integral for all the problems. So you don't have to constantly redo your integral for every step.
Quick question. Where did we get the 0.5 from?
Because that would be the median means that half the probability is cut directly in half. So half of it would be before it, half would be afterwards. So that's where the
So we're just using the 0.5 as like a representative of half.
right. Yep. Exactly.
So this median, right? This is based obviously on the number of data points as opposed to the sum of all of the hours of each of all the light bulbs. I'm assuming being that some light bulbs, if the median is so low compared to 1,000 hours, which is the average, that means a bunch of the light bulbs, or like the half of the light bulbs, more than double. They get closer to 2,000 hours to make up for the fact that the median is so low.
Yes. Yep. So you're gonna it's because of the way that the mean and the median is, this one is definitely skewed to the right. You're gonna have, or yeah, skewed to the right. You have more values further to the right that pull the mean in that direction.
Or well, not more values, right? Because it's 50%, but those values are
Right, not more light bulbs. The light bulbs last longer.
right.
So yeah, 50% of the light bulbs will burn out before 693 hours. The other half of the light bulbs are going to last longer than that, and some of them quite a bit longer than even the 1,000 hours. We figured out in the first problem that over a third of them actually last for more than 1,000 hours. All right. Let's do another one. So it says an online retailer has determined the average time for a credit card transaction to be electronically approved is 1.7 seconds. So again, same concept as we just did in the last problem. It's f of t is 1 over 1.7 e to the negative t over 1.7. So that's going to be my equation for this. So got to find my integral of it. So I would just do the integral out, have that, and then I can plug in, do all the rest of the problems out. So I'm doing my integral of 1 over 1.7 e to the negative t over 1.7. So one thing, if you do a few of these, you're going to start to notice a pattern forming. The pattern is this basically cancels out the number in front. So this answer is just negative e to the negative t over 1.7. So because if you do the u substitution on it, that's going to give you 1 over 1.7 dt, which is going to cancel that part out anyway. All you're left with is the negative sign. And that's why there's a negative sign in front. So A is just negative e to the negative t over 1.7. And we're evaluating it from 0 to 1. B is negative e to the negative t over 1.7. And we're evaluating it from 3 to infinity. All right. Let's do those two, and then we'll look at C. So we go over here, again, using Desmos. So I have, the 0 is going to be 1, so I don't really have to put that one. So negative e to the negative, what was the first one? 1 second.
It's 1.
Got it. Plus 1. So I get 3 decimal places. So 0.445 for that one. And then the next one, the infinity one's going to go to 0. So it's just 3 seconds. Then it's the positive version of it. So 0.171. All right. The next part, C, says, what's the minimum approval time for the slowest 5% of transactions? So for this one, we have our thing. We just don't know what the top value is going to be. If it's the slowest 5%, what's going to be the percent? What's going to be the probability that I'm looking for? If it's getting progressively higher, what's everything all the way down to the very end going to give me?
0.05.
The opposite direction. 0.09.
Oh, slowest, right.
95. So we're going the other direction. So basically, by this point, 95% of all the transactions would have been done. That's where the 0.95 comes from. So the 0 one is just going to give me the 1. So I know I'm going to add 1 to whatever I have. So we
Wait,
get.
does that mean that we'll then 1 minus all of this?
No, so it's going to end up being +1. So I'm going to write it out in a second. So this becomes negative e to the x over 1.7 plus 1 equals 0.95.
No, I know. I'm saying right now we're saying what is the, so by making it equal to 0.95, we're saying, you know, what is the approval time or the average approval time for 95% of all transactions, right?
Yeah, so there's my curve.
Okay,
I'm looking for this piece over here where that's 5%.
right,
So that means the piece over here, which is where I'm calculating for, is the 90 or 0.95%.
right. So then to get that piece, we do 1 minus the 95 percentile, right?
Yeah, I'm going to bring the 1 over. So I'm looking at, in essence, I'm looking at this number all the way up because I'm looking for this value right here. I'm looking for that value. So to get it, I could either do the X all the way to infinity, which will give me that side, or I can do 0 to 95, which is going to give me this side. That's easier. Because I have the 0, which is going to give me 1. So instead of having to deal with the infinity side of it. Although it doesn't really make much difference because I'm going to bring the 1 over.
Oh, I guess it's just the way that it's worded. So they're saying, so for the slowest 5% of transactions for all those, what's the fastest those slowest will run?
Right. What's the minimum approval time? So that's this value right here.
It could be a lot longer, but that's as fast. If you're at the slowest 5%, that's as fast as the slowest 5% will go.
Correct.
That's such a challenging wording.
Yes. But if you're going to try to sell this to a company, you're going to say that 95% of my transactions will process within this amount of time.
Right.
So, and honestly, that's like when you say 95% or 99% or something like that, that's the customer really wants to know that piece of information rather than 50% of my transactions are going to produce in this time. It's like, so this value right here is actually the one they're probably going to advertise and the one they're going to try to optimize for in essence. So this, if I move a few things around, just to simplify this a little bit, I get x e to the negative, if I go that equals 0.05. So now I do my ln. So I have x over 1.7 equals ln of 0.05 and multiplied by the 17. So x equals 17, or not 17, 1.7 ln of 0.05. That's what I'm going to plug in my calculator to get my answer. Seven. I lost the negative sign. I lost the negative sign. That's okay. Oh, I lost the negative sign up top. That's where I lost my negative sign. So this one's coming out to be 5.093. So 5.093. What's this be? So 95% of my transactions are processed with in under 5 seconds. The crazy thing about it is when you sit there and swipe your credit card, 5 seconds is an eternity.
Yeah, you start looking at the cashier like, what did you do wrong?
Exactly. It's like 5 seconds. Like it doesn't seem like it'd be that long, but it's an eternity. All right. Let's do this one. So this one, actually, this one's really simple because it's all computer. It's all going to be in Desmos. So the only thing with this one is you just got to figure out which equation or which where you're plugging all the numbers into the equation. So we're using this one. I don't think what it actually works today. So we're using that equation right there. That's the normally distributed curve. So when I plug in my values, that little symbol, that is your standard deviation. And that is your mean. So I have 1 over 2.8 square root of 2 pi e to the negative x minus 69 squared over 2 times 2.8 2 times 2.8 squared. And then A is the integral from 64 to 74. And B is the integral for, it says more than 6 feet tall. So that's 72 to infinity. So for this problem, it's just plugging the numbers into that formula, and then we're going to throw it right in Desmos to get my answers.
Wait, did we forget the 2 on the bottom there?
Nope, 2's right there. 2 times 2.8.
Oh, gosh. Thought that said 2.28.
That's a problem with using dots for multiplication and when you're looking at algebra. Really easy to think about it as a decimal point.
Sir, how did we find the integral for B?
It's the it says more than 6 feet tall.
Mhm.
So 6 feet is 72 inches
Oh, okay.
or more. Let me clean this up a little bit. That's better. All right, let's go to Desmos. So, integral. So 64 to 74. 1 divided by a second. Oh. That sure was on the outside. That's better. All right, so the first one I've got, and it wants it to 3 decimal places. So 2 or 9 to 6. So about just over 93% of all males will be between 64 and 74 inches tall. So 5'4" and 6'2". Now, when you're doing the infinity one, you can't put it in. Well, actually, in this one, I think you actually can put infinity. But just pick an insanely high number. It doesn't make a difference which number you pick, just make it really big. So this one comes out to be 0.142. And that's how you do those. All right, do the differential equation, the separable equation. All right, so your separable equations are ones where I have two functions, the g of x function and the f of y function, vice versa. Basically something that I can easily split the x's and the y's out so I can put them on either sides and look at the integral of both sides. We've got d over dt equals 6 plus t to the fourth over ut squared plus u to the fourth t squared. So the first thing we have to do is we kind of got to get this, the bottom part, I've got u's and t's. I got to kind of manipulate that a little bit to get the u's by themselves. So the top, we have the 6 plus t to the fourth. And the bottom, I'm going to pull out a t squared. So I have u plus u to the fourth there. So now I can pull out the u to the on the other side. So I have u plus u to the fourth du equals 6t to the negative second plus t squared dt. And now I do my integral of both sides. So this becomes u squared over 2, u to the fifth over 5 equals negative 6 over t plus t to the third over 3 plus t. And that transfer can't go any further. And this one doesn't have an initial value, so the c has to stay in the problem. Okay, next one. I know, it's getting late. Almost done, 2 problems to go. All right, so I've got dp over dt equals 7, the square root of p t. So this is one of those ones that actually is easier to split up than it looks. Because I can split this to do the square root of t or p and the square root of t. So I get dp over 7 square root of p equals the square root of t dt. Or actually, I can leave the 7 over there. It might actually be easier than having it down the bottom. So put that over there. One less thing I have to worry about with the division. So because I take that square root apart, remember, you multiply to put them together, so I can split them apart the same way. So we do my integral of both sides. So the integral of p to the negative 1/2 ends up being 2 square root of p equals what is yeah, 14 over 3, and then it's t to the 3/2 power plus d.
Like, could we do the left integral again? So if it's p to the negative 1/2, then you add that, so it becomes 1/2, right? And then divide it. So it would be not 1 over half, 1 over 2, right?
When you divide by 1/2, it's the same as multiplying by 2. All right, now this one gives me my initial value. So we have to plug in to find C. So I got 2 square root of 6 equals 14 over 3 C. So 2 square root of 6 minus 14 over 3 equals 2. So I've got 2 square root of p equals 14 over 3 t to the 3/2 plus 2 square root of 6 minus 14 over 3. So I'm going to divide this whole thing by 2. So I get square root of p equals 7 over 3 t to the 3/2 plus square root of 6 minus 7 over 3. And then I got to square both sides. So p equals 7 over 3 t to the 3/2 plus square root of 6 minus 7/3 squared. And that's my final answer.
Wait, what happened to the t's up top?
This t?
No, up above that. Why did we not have any t's there?
Oh, because I plugged in 1 and 6. So t was 1. And the p was 6. I was trying, this part up here, I was trying to find c. So I was using the p of 1 equals 6.
Okay, so
So p
t,
is 6. And 1 to the 3/2 or 3 over 2 is still 1.
where P equals 6 and T equals 1.
Yes. Okay. So all I'm doing is I'm just replacing that T right there with 1. And that P with 6. To find C. Because they gave me my initial condition. Because we're running out of time, I'm going to put the answer for this one in there, the explanation and the written out words for it. I'm going to upload the video and the notes to it. If you would like, I can come on tomorrow I can be on at 5 o'clock tomorrow. So I can do like an hour or so tomorrow if anybody has any other questions, I want to hop on.
At what time?
I'll be around 5. Same
All
time.
right.
So, all right,
Thanks, Professor.
problem.